In this video, we will do a bunch of examples of converting a Riemann sum to a definite integral. So let's start with the first one. Write the definite integral that produces the same value as this crazy looking thing. This is the limit as n approaches infinity of the summation from 1 to n of 5 plus 3i over n, all cubed, times 3 over n. Okay, so now this is the limit definition of a definite integral. It actually represents the area under a curve, the exact area. It's amazing that people use this before our fun little integration formulas were developed. Man, this was like back in the 1600s. Like people were doing this with their brilliant minds. They created this formula. It started out using just rectangles like we've been doing, and the estimations were really bad because the rectangles were giant. Well, now we're getting into exact area because the rectangles are tiny, the widths are really small. So let me explain. This is the generic formula for what we're looking at. This section represents the area of a rectangle. This first piece is the height of each rectangle. It's the y-coordinate. Notice that it's function notation, f of a plus delta xi. We'll get to that part in a minute, but that's our height, that's our f of x. And then our width is the delta x. This summation piece represents the sum of consecutive terms. In this case, each term is the area of a rectangle. So we have areas of rectangles being added. And because n is approaching infinity, we have an infinite number of rectangles here. So our rectangles reach infinity. We have an infinite number of rectangles that we're finding the area of, so it essentially is giving us the exact area under a curve. It's pretty amazing. And now this piece on the inside of this function notation, again, this is going to be our y-coordinate because it represents f of x, but the inside is the x-coordinate. It's what you plug in to f of x, and that gives you the x-coordinate of every rectangle that you're going to use to find the height. And in this case, this is a right-handed estimate. So it kind of looks like this. This is the situation. We have from A to B, the area under our curve. So there's our A x-coordinates. If you add delta x, this is where the first rectangle would go. And this would be like our first area. So this is when I equals 1. This is our very first one. So this is A plus delta x times 1, or 1 delta x. And then if you do it again, this is now A plus 2 delta x's. And this would give us the x-coordinate that we would use to plug into our function, f of x, like whatever this function is. We would be able to find the height of this rectangle. And it just keeps going. So this is when I equals 3, it's A plus 3 delta x's. And we keep going until we get to n, which essentially is infinity. So this would just keep going forever and forever and forever because this is really infinity. This goes on. These are tiny, tiny little rectangles. It's pretty crazy, but that's the situation. Okay, let's get back to this problem. So what we need to do is start out, best thing is to find delta x. This piece is fixed always. So when we're going from like this to a definite integral, this will always be here. This is the part that we're going to use to find our answer. So from this to this, step 1, find delta x. We're going to use this piece, which is right here, to figure out a little bit about a and b. It doesn't give us what a and b are equal to, but it does tell us that the distance between a and b, so b minus a over n, in this case is 3 over n, it tells us that the difference between these two numbers is going to be 3. Again, I don't know what a and b are, I just know that if I looked at the two of those numbers, the distance between them is 3. The difference between them is 3. So it could be like 1 and 4. It could be, 25 and 28. Who knows? Okay, so we have that much information. Let's look at this piece now. So now this is our f of x. If you look at the big picture of this, like forget that there's weird stuff on the inside. Look at what's happening. It's something being cubed. That's your f of x. That is going to be your integrand. You look at like it's a composite function. Remember, you have the x coordinate on the inside. The f of x is the actual thing that you're finding the value of. So because we have stuff on the inside of parentheses and it's all being cubed, our f of x is x cubed. The inside now gives you your a value. So look at what we have here. A is 5. Delta x we found was 3 over n, and then the I is always there. Because the I, remember, is like kind of like the place value. It tells you which rectangle we're on. The first one, the second one, the third one, the fourth one, and so on. So now you know that A is 5. The distance between them is 3. This has to be 8. So here's a summary. We have our delta x is 3 over n, A is 5, and x cubed is our function. Now you have enough information to put it all together. Okay, let's do another one. I'm going to do quite a bit actually. Okay, same thing. So we have our limit definition, summation notation. Remember, this is the fixed part. This one stays there all the time. This piece is the delta x. So the distance between our a and b is 2 this time. This is our function. Look at big picture, what's happening to it. In this case, it's something being square rooted. So our f of x is the square root of x. Now take a look at inside of it. This gives you the a value, which is 1. So if you know that a is 1 and the distance between a and b is 2, then that means b has to be 3 because the distance between 1 and 3 is 2. Hopefully that makes sense. And function is square root of x. So here we go. You just put it in its place. The f of x piece goes here. A is 1. The distance between them is 2. Done. Okay, another one. Okay, this one has more pieces, but it's the same process. So delta x is the inside here. This piece, the arrow is not pointing to the right thing, it looks like. So the distance between a and b is 4. Look at your f of x function. Now this time there's more than one piece to it. It has a subtraction sign in it. But notice the 4i over n is there twice. So that's the piece that's being plugged in. Big picture, 4i over n is being squared, and then 4i over n is nothing's really happening to it. It's just being subtracted. So it's x squared minus x in this case. And a, check this one out. This one's different. There's no plus. Like it's a plus delta x times I, but there's no addition in this. So a is 0 this time. There's no adding. So here's our summary here. So the distance between a and b is 4. And because there's no addition, you still have the delta x, which is 4 over n times I piece. That'll always be there. But in this case, a was 0. So if a is 0, then b has to be 4 because of this. And our function is something being squared minus that something, which is x squared minus x. Done. Okay, let's do another one. So we have the limit definition, -1. Notice you can start seeing things now. Like this is your a value right away, and the distance between a and b is going to be 1. So that helps a lot, just knowing that much. Okay, so delta x is 1 over n. Our function in this case, a little different though, because notice nothing is happening to it. It's not being squared. It's not being square rooted. There's nothing going on. It's just x. And that's the tricky part about this one. So once you can see that there's nothing happening to this function, it's just plain old x, and now you can go inside of it and see that a is -1. Now you have everything you need to write the definite integral. A is -1. The distance between a and b is 1, so this has to be 0. And this is so not the right one. How did that happen? Let me back up. There we go. Sorry about that. So this is -1, this is 0, and our function, because nothing is happening to it, is just plain old x.